Today, I'd like to talk to you about the research project that we did over the last 8 years at Oracle, and that's now becoming a product and a new way to run programming languages. And the name of our project is GraalVM. So the idea behind GraalVM, or what we wanted to do here, is to really, one of the main things we think is the case here is that the world is polyglot, meaning there's many different programming languages that people are using. This is from statistics from the TOB index, and it shows, well, yeah, Java is kind of the #1 programming language, but there's many other programming languages that are used often, including Pison, JavaScript, and so on. And with my background of working on Google V8 and also then on the Java virtual machine, I thought, well, why don't we create one platform that can run all the languages at the same time? And this is when we started 8 years ago this research project, and back then this was a paper we published on one VM to rule them all, meaning one virtual machine that can execute all programming languages. So this is what's the general vision behind GraalVM, is to create one execution platform with many languages. And our goal here is that you can use GraalVM all across your stack, all across your cloud stack or your execution stacks. And we have two goals. One is to run programs efficiently. So GraalVM is high performance, so trying to create better performance for your programs. And the second is to make developers more productive by allowing them to use multiple languages in the same program, or also to allow them to basically use the best language for the task. So this is kind of the abstract thing behind it. And what does it mean in concrete terms? In concrete terms, what is GraalVM? One of the things it is it's a drop-in replacement for Oracle Java 8 or Java 11. So if you have any program that would run on Java 8 or Java 11, you can run it on GraalVM, and it will run with a different just-in-time compiler compared to the standard Oracle Java, and it will run faster. So usually when people use the word compiler, they mean Java C, like for example, or Scala C, or something like this. And these are compilers that will translate your Java sources to Java bytecodes. When I speak about the term compiler, I mean a compiler that takes the Java bytecodes and creates machine code from it. So this is usually in Java, it's a just-in-time compiler, meaning it will do this process while the program is running. The second thing our GraalVM can do is it can do this compilation of Java bytecodes to machine code, not only just in time, it can also do it ahead of time. And this is something we call native images, and allows you a new way to run Java that is closer to the performance characteristics of running C, C++, or Go or Rust, for example. Because here we do all the compilation ahead of time, and then the final binary is already executable without any additional interpretation or just-in-time compilation. It's the second thing GraalVM gives you. And the third thing GraalVM gives you, it gives you high performance for other languages as well. You have an implementation of JavaScript, Python, Ruby, and R on top of this system, and we allow you to have these languages interoperate with the host environment and interoperate with each other. So these are the three things what GraalVM can give you. In a slightly more visual form, this is the same thing, now a little bit more visual. We can run the JVM-based languages, just like you usually would run them in the context of OpenJDK. So you cannot just run Java, like anything that would compile to Java bytecodes, including Scala, Kotlin, etc. We have these implementations for Ruby, R, Python, JavaScript. And then we have something in GraalVM that also allows us to run statically compiled languages like C, C++, or Rust. The way we run those languages is that we are compiling these languages to LLVM bitcode. So we use the LLVM project to do this. And then we would run those languages on the GraalVM platform. And just last week we added WebAssembly as well as one of the ways you can run things on GraalVM. So this is also supported now. But you can see here kind of our ambition to have GraalVM really for almost any language here, because it's any language that compiles to Java bytecodes, any language that compiles to LLVM bitcode, any language that compiles to WebAssembly, and then Python, R, JavaScript, Ruby in addition to that. We can run these languages in the context of OpenJDK, but we also have an integration with Node.js. So you can also run it in the context of your Node.js platform or application. You have an integration with the Oracle database, so you can execute stored procedures with GraalVM. And this is generally one of the things you want to do with GraalVM is to embed it into data stores. For example, Spark, Hadoop, one of these things, to combine it with GraalVM so you can execute your queries in a GraalVM-based language. And then we finally have native image, which is the ahead of time compiled mode of GraalVM. Here we can run without any other platform surrounding it, but just as a lean and small footprint binary. And so this is one of the things that is, so when you run GraalVM, you can have Java, Scala, Ruby, Kotlin. You can run it like normal JIT, like you would usually with Java. Or, and this is a new way how to run GraalVM, these type of languages, with this ahead of time compiled mode. And I will later demo like what this can do for this type of applications. Like the way it works is instead of running Java and then give the main class, you run a native image command and give the main class, and this will create an executable for you that you can start multiple times. And will start very fast. So on the JIT mode, GraalVM replaces in the OpenJDK the default just-in-time compiler, and in this way we create better performance. This is a performance overview of GraalVM here of various workloads, some Scala workloads and some Java workloads. There's different frameworks in here. FileMaker, for example, which is a Scala load balancer. There is also Neo4j here, which is a graph database. We have some workloads here that test GraalVM. Here higher is better, and this shows the speed up we get over the standard way to run this type of JVM-based applications. This JIT mode, this just-in-time mode, is currently in production at Twitter. So Twitter is using Scala for their tweet services, and they are running their tweets via the GraalVM compiler. So the programs processing the tweets are compiled with the GraalVM compiler, which makes the processing more efficient for them with lower latency for users of the Twitter service and smaller garbage collection requirements. Another point where we use the JIT mode in production is in the Oracle Cloud Infrastructure, where we have higher efficiency for some of the core services by using the GraalVM Enterprise Edition, and also lower the garbage collection times. So this is for the just-in-time mode for GraalVM. And so in addition to the just-in-time mode, as I mentioned, we have this ahead-of-time mode for Java-based application. This is a new way to run Java application that is very different from the one that you would currently be used to in the JIT mode. The way this works is that we do take the application sources, the libraries the application uses, the JDK functions the application uses, and some substrate virtual machine, meaning a garbage collector that we have written ourselves, and we do a program analysis on this piece of software. And that program analysis is a reachability analysis. It's a points-to analysis that is trying to figure out all the code that is reachable from your program's main entry point. You can think of it like you start from the main entry point and then you expand the reachable methods and code until the expansion is no longer, like it's an iterative process until the expansion is no longer adding additional code. After we do this analysis of what is reachable, we compile all of it into a final executable where everything is already precompiled, so everything is turned into machine code already. And this executable can then start up very fast. This is a new way how to run Java-based applications because currently it's mainly running always in JIT mode. When would you do this? So the reason to do this type of ahead-of-time compilation for Java is when you care about the startup time of your application, because the startup time gets a lot faster than before, and when you care about the memory footprint, so when you care about the amount of megabytes that is occupied by your process. Specifically, this type of way to run it in a cloud or microservice infrastructure means you can serve more requests per megabyte second, meaning you can serve more requests while occupying a certain amount of memory for a certain amount of time. Like this is what a Microsoft developer advocate on this question had to say on Twitter. This is Bruno Borges. He is the lead Java program manager at Microsoft. And header says like, well, this type of way to run Java code gives you a performance characteristic like Go in terms of startup, but you can still use your Java libraries, you can still use Java for this. So it is basically allowing you now for Java, you have a choice, whether you do the just-in-time compiled mode or whether you do this ahead-of-time compiled. So what I have here as a demo for this ahead-of-time compiled mode is I have here a Java web service. So it's using Micronaut. It's one of the Java web service frameworks. And what I can do is I can run this with the normal Java -char, and then I do here. This is my application, and I can run it. And yeah, after 2 seconds, it started up on localhost. This now my Java web server is finally up and running. I can go to my web browser and check one of the REST endpoints this web service exposes. And now I've served a single request on this web service here. Okay, simple Java web service, one REST endpoint, and it gives different results on different requests. So what I did before here, I created a native image, this ahead-of-time compiled mode from this Java web service. And this is here a final binary now. It has here 50 megabytes, but it includes everything that you need to run this application, including the garbage collector, including all the libraries and everything. So what I can do now is I can just start this application. And what you can see here is like, I can start this here in about 20 milliseconds. So this is very different here, and I can still check that this works in the browser. And it is, here I can go conferences random, and it gives me the REST endpoint. Okay, so I can do a slightly more sophisticated test here. I have a startup test script that is starting the process and then checking how much time it takes until the first request returns OK. And I can do here now my startup test java -char build libs complete jar. And so this is starting here in 1 second here now, but the total CPU time use is actually 3 seconds. The reason for that is that while you start up your Java application, the JIT compiler will take additional CPU resources to compile to machine code. So the total CPU time used just to serve a single request here for this web service is 3.6 seconds. And now I can do the same startup test with my native image. And the total CPU time used to serve the first request is 30 milliseconds. This is a 100x difference to serve the first request. Now, I can do a slightly more sophisticated test by doing a load test. So the load test that I have here is it's a slightly more complex script, but in the end, it is serving 10,000 requests on each iteration, and then checking the amount of CPU time used and memory used by the process using the PS tool. So I can now do the load test here. And let's here now configure this to some values, because we also measure our memory. So we configure this to 128 megabyte of memory, which should fit the application. Let's try this first with the native image. Okay, here it seems to work. Let's see. So this is running the script with native image here on the laptop, and it's running 10,000 requests on each of these iterations, and it is showing how many requests you can serve on 1 CPU seconds, and what's the size of the application in terms of memory. You can see the memory occupied by the application is very low here with native image. We only take 40 megabytes of memory total on the whole application process. And let's now see if this also works here. Okay, so now we go with the regular JIT Java, and what you can see here is I've configured this the same way, both with a heap size of 128 megabytes, but the resident set size of the application, so the total memory occupied in the process, is 180 megabytes. So it's much, much higher. And so we are serving, because we're in JIT mode, so the JIT compiler produces better machine code at the moment. So we're serving more requests per CPU seconds, but in terms of requests per memory seconds, per megabyte seconds, so in terms of requests per occupied memory, we are much lower than the native image version. Also here, the JIT mode takes a very long time to warm up. So for the first 20, 30,000 requests, even in terms of CPU seconds, the native image is better, meaning the ahead of time compiled mode is better. And this just shows that, like, you can hear 4 web services, also in the embedded space, have a very different runtime characteristics for your Java. So on native image support, for this support of this ahead of time compiled mode, we have several frameworks that are supporting this ahead of time compiled mode for Java microservices. One is Micronaut, one is Helidon, and one is Quarkus from Red Hat, where they are targeting this GraalVM native image as one of the ways to deploy your Java web services. And as I showed in the demo, the startup time goes down like by huge amounts, like up to like 50x faster in startup, and we also have a lower memory footprint. So here, for those web services, you usually get a factor of 5 lower in terms of memory footprint. This is showing the same example now in ahead of time compiled mode and JIT-compiled mode, where it shows that on the ahead of time compiled mode, you're spending the CPU cycles only when you actually serve a request. So this is serving 4 requests. And only when the request actually goes off, you're spending CPU cycles, where in the just-in-time compiled mode, you spend a lot of CPU cycles at the beginning, and also later on when you do more just-in-time compilation. So currently, in these 2 modes of GraalVM executing JVM-based applications, you can choose between the ahead-of-time compiled mode with lower memory footprint, better startup speed, or you can choose this just-in-time compiled mode, which gives you higher throughput over the very long run. So if you have a very long-running application, or it also gives you better latency if you have a very large heap. We're currently working on improvements to our system to make the ahead-of-time compile mode as efficient as the just-in-time compile mode. So one of the things the just-in-time compile mode does is it does profile-guided optimizations, but the just-in-time compiler will check out how the application behaves, and then from this derive like optimizations. What we have for our ahead-of-time compiled mode is profile-guided optimizations, but you have to do them ahead of time. So you can create a binary of your Java application that is instrumented, and then you run this instrumented binary on example test workloads, and this will create the profile file, and you can feed this profile file into generating a new image with the optimized binary. In this way, one of the advantages this has is that you can optimize for the cases you care about most. So you can make sure that the corner cases or whatever you want to have fastest is optimized for your application. We do support almost any platform via the LLVM backend that we have for native image. Usually you would create a binary out of native image, but you have an option for you to create LLVM bitcode out of your native image, and then this LLVM bitcode can be compiled further to specific platforms with the LLVM backends. One of the platforms that we're targeting there together with Gluon, currently with Gluon Mobile, is the mobile platforms. So we have, for example, here Java running fully ahead of time compiled on iOS devices, and we also have it running on Android. You can use this on desktop to reduce your startup time and memory footprint also for your desktop application. And in these scenarios, your Java is fully ahead of time compiled on the target OS, meaning the final resulting binary on these mobile devices are starting very fast because there is no interpretation overhead. There is no just-in-time compile overhead on these devices. And we can, with this system, specifically also target much smaller devices than what would currently be possible with Java Mobile, because of we have no additional requirements for memory for compilation or for loading classes, etc. So the memory requirement really is practically only your application payload memory, and there is no overhead associated with it. So one of the things GraalVM can do for you is the polyglot aspect. So it can also, like I now talked about these two things, just in time compiled, just get faster for JVM-based languages, and ahead of time compiled, this new way to run JVM-based languages on low footprint. And now the third aspect of GraalVM is this polyglot and embeddability aspect. So one of the things you can do with GraalVM very easily is embed other languages into Java. We have our JavaScript engine, and you can then call to this JavaScript engine from your Java code. You can also add this JavaScript engine into your native image. So your native image can still dynamically run JavaScript or Python code, for example. This is an example source code where we have Java running and then we're calling out to JavaScript. We can run embedded in the Node.js platform. We are there fully reusing the Node.js architecture, and we just replaced the V8 JavaScript engine with our GraalVM JavaScript engine. This GraalVM JavaScript engine is, by the way, like up to the latest JavaScript standards, so we are as compatible with respect to JavaScript as any of the others, including the Chrome JavaScript browser. Why would you use our Node.js? The advantages that we offer over the standard Node.js distribution is that we allow you to have Java interoperability. So from your Node.js application, you can call to Java libraries, for example. We have polyglot capabilities, so we can call to Python, Ruby, R from your JavaScript, and you can run on a JVM your Node.js with that can be specifically interesting for large heap requirements. So if you have a heap of 10 GB or more, like our Node.js implementation is performing better than the V8-based Node.js. We do have support for statistical language R. We implemented R on top of our platform, so you can run like R blocks and R packages with GraalVM. And we are adding at the moment Python to the platform as well, where Python can run on GraalVM and participate in this language interoperability. Here is an example of Python calling an R module, because you might want to reuse a certain piece of R, for example. In the Python space, we are focusing on NumPy and SciPy as the first target, and we are also specifically focusing on creating an implementation that runs SparkPy. So where Spark itself is written in Scala, so it can naturally run on our JVM-based platform, and then we are integrating our Python implementation to run your Python script that you run with PySpark. Python is at the moment still early in the development. We are doing the Python implementation since about 2 years now, and we can run basic tests, but we are still working to make it more complete. As for Node.js, we have one example here where you have a Node.js application and it can call out here to Java code. It is using here the Java multilingual integer, and it can also call out to other GraalVM languages, here for example the R code. And on the right you can see a plot created by R and then displayed by JavaScript. And then for GraalVM, all of these languages execute in the same environment, with the same debugging tools, with the same profiling tools, with the same compiler. And they can also share data structures and have data structures flow between languages. We have polyglot pooling for that, so you can have polyglot stack traces, so you can have stack traces that span across languages. We have our own tool for this, VisualVM, but we also integrate with Visual Studio Code and with the Chrome developer tools. So you can debug your programs also in the Chrome developer tools. And we have a polyglot heap viewer where you can see objects here from R, JavaScript, and Ruby in the same heap view. One of the projects that is integrating with us is Wuerthinger project. They have like a JavaScript implementation, which is a little similar but more lightweight than Node.js, and they're currently actually like one of the fastest web frameworks according to the Tech and Power frameworks. They are running their JavaScript and their Java on top of GraalVM. We have a collaboration ongoing with NVIDIA, NVIDIA has this project, this collaborative project, GraalCUDA, which stands for GraalCUDA, and it is a project that is allowing CUDA as an additional language into the GraalVM ecosystem, so you can share data structures between your GPU and the languages you run on GraalVM. So we are expanding here to make sure you can run some of your code also then on the GPU with this GraalCUDA. To summarize here, I've talked about many parts of GraalVM and what it can do. Here, this slide shows a little bit of what is currently production ready. So what is currently people are already using in production. What are things that are experimental at this stage and will be soon production ready, and what are things that are still in the works. So production ready at the moment is to run your Java applications, Scala, Ruby, and Kotlin applications. And you can certainly test them if they run faster on GraalVM in the regular JIT mode. This is what is running in production on Twitter or the Oracle Cloud, for example. Production ready is our JavaScript implementation. As I showed, we are fully standards compatible. We are testing every week with 110,000 Node.js modules, so we are sure that we are compatible also with Node.js. This JavaScript implementation is, by the way, used in production at Oracle's largest SaaS application, which is NetSuite. It's a SaaS application, and we allow users of that application customize it with JavaScript. And then GraalVM is used to run this JavaScript. Production ready is native image. This is ahead of time compile mode that I showed that makes it possible to run JVM-based languages in a very low footprint environment and with fast startup. This is also the thing that can help with running on embedded devices or mobile devices where startup and footprint is a relevant factor. VisualVM is our production-ready profiling and polyglot profiling system that can be used. Experimental is currently our Ruby implementation, our R implementation, and our LLVM toolchain. So the implementation of LLVM-based languages on top of GraalVM with C, C++, Rust. And in the works at the moment is our Pison implementation. We are very heavily focusing on this at the moment as Pison is very popular. We have a Visual Studio Code plugin in the works that make this programming on top of the platform simpler. GPU integration in collaboration with NVIDIA to enable CUDA code to enable sharing of data structures between the CUDA-based device and GraalVM languages. We have the WebAssembly front end, so a running WebAssembly has been added last week, and we have the LLVM backend to support more different platforms with GraalVM. And GraalVM is an open source project. You can find it on graalvm.org and on GitHub. And we also have an Oracle associated product with it that comes with the regular enterprise level support, etc. So we have a dual strategy here where we have an open source version of GraalVM as well as the enterprise version. So the value proposition, why would you consider GraalVM, or what would be reasons to run on GraalVM? One is the high performance in JIT mode, where we have a better just-in-time compiler to translate to Intel machine code. We also have an ARM version of GraalVM, ARM 64-bit support. The second value proposition is, in case you're interested in a low footprint environment, we offer this ahead of time compiled mode. So if that's of interest to you, low footprint fast startup, then this is the second possible value proposition of using GraalVM. The third value proposition is the language interpretability and polyglot. We have several companies use this for combining languages. One of them is TalkDesk, another one is the Dutch police, who are using R and Java in combination with this platform. Because they have some data scientists who want to write their code in R, but they also have some programmers who want to write their web servers and services in Java, and then they combine these two things and run on GraalVM. The fourth value proposition is the simple embeddability in native and managed programs. This native image that I showed, you can also link it with your C, C++ program. So similar as you can embed, for example, V8 into a C++ program, you can embed GraalVM into a C++ program. This is, by the way, how Node.js was started. When Node.js was started, basically with V8 being integrated into a C++ libuv library, right? And when you do this type of integration with GraalVM, like the benefit you would get actually is that you can leverage all of the GraalVM languages in the context of this embedding. So you're not fixed to JavaScript, you're not fixed to R, you're fixed. Like GraalVM is this universal tool to run all these languages. And generally, we see ourselves as a value-add ecosystem where you can run multiple languages in multiple embeddings, and we provide language-agnostic optimizations, tooling, interoperability, security as part of the core GraalVM platform. And we are welcoming third parties to add their own language or add their own language-agnostic tools or their own embeddings to this platform. We have currently many such both commercial and open source entities adding languages or embeddings. In terms of languages, a commercial entity that is evaluating the use of GraalVM for their platform is Goldman Sachs. They have a specific language called Slang for their risk analysis platform, and they are working on porting this language on top of GraalVM so they can benefit from the optimizations, tooling, and interoperability of the platform. In terms of open source projects, for example, we have a SmallTalk implementation that is also added on GraalVM. And so we basically welcome other players that want to participate in this ecosystem. So yeah, it's 100% production ready. Here is a screenshot from our open source page on GitHub. We have about 3.6 million lines of code that my team is managing on GitHub. You can follow us on Twitter for updates, and we have a public Slack channel as well. If you have questions, you can be directly connected to the team with a public Slack channel. And with that, I would like to thank you for your attention. Thank you very much. I'm open for questions if there are any. Thank you.